Okay, very good morning, everyone. We will wait for 1 to 2 minutes so that someone will join, and we will start. Yeah, we will wait for 1 minute so that someone will join, and then I will start the today's session, right? So now we will start. Actually, in the previous lecture, we will discuss about the breakdown mechanism and as well as the Townsend mechanism, and we will also discuss the breakdown with an avalanche discharge. That means what will be the Townsend mechanism in the gaseous dielectrics, obviously, because we are under the gaseous dielectrics part. Okay, and we will also discuss the growth of the conditional current in the gaseous dielectrics. Okay, so what will be the various breakdown process will be takes place due to the avalanche discharge, that we will discuss, and that we will consider as a Townsend mechanism, right? So we will also discuss in the previous lecture that we have a different kind of effect which will be shown in the avalanche discharge breakdown. What is a positive ion effect, photon effect, and the metastable effect. Okay, we will also discuss some general conduction current voltage characteristics before the breakdown will be occurred. Okay, and some characteristics of a current voltage waveform. Okay, current voltage pattern. Okay, that we will discuss in the previous lecture. Okay, so today we will discuss the voltage current characteristics of a helium that will measured by the scientist Rees. Okay, RWS. Okay, so the characteristics between the voltage current of a helium. Okay, helium is a one type of gas which will be available inside the dry air. Okay, or the atmospheric air. So what will be the characteristics that we will see? Okay, accordingly, what will be the uh, voltage current characteristics for the helium gases that we will discuss today, right? So directly I will share my screen so that you will check. Hmm. So okay, so now we will share something so that yes. So previously we will discuss about the breakdown of an avalanches. Yes, I first draw these things and then I will told you. Right. Yes. So we will discuss about the breakdown of an avalanche discharges and the growth of a conduction current in the gaseous dielectrics. We will discuss the three different effects which we will see. We will see the three different effects, right? Okay, and also we will discuss about the characteristics of a general condition current voltage characteristics before the breakdown which will have been occurred, right? So what are the different characteristics? See, some of one is coming, I think. Okay, so yes, so these characteristics we will already seen that's in particular current voltage profile. Okay, so now we will consider the voltage. 1 second, right? 1 second. हाँ अनिल सर. हाँ सर थोड़ा देर बाद में कॉल कीजिएगा हम थोड़ा क्लासेस ले रहे हैं. हाँ ठीक है सर. ओके. हाँ हाँ हाँ. Ah, yes. Okay. So in this part, that means we have seen the characteristics of a helium gases, which will be defined as an He of that particular Vi characteristics, or we can say that it's a Ui characteristics. Okay, so that we can see, right? So that will be the current profile. Okay, the axis, and in this axis we are considering the voltage. What we will see that when the voltage is increasing, so for that cases our current will be increasing somehow. Okay, and it will be drastically increased after a certain amount of voltage which will be applied to the particular electrodes, right? So in this particular stage, after this particular stage, when the current will be 20, okay, at the current when it will be 20 ampere, okay, 20 ampere. So for that cases, your voltage should be supposed to be 750 volt, right? So after that, what is happen? It will drastically increase the current. Whatever the values of the voltages is, whatever the values of the voltage, we will see that current will drastically increase. Okay, why this is so? That we will discuss on this particular characteristics, right? So why this will happen? So it is written that it will be distinguish features of a breakdown that the voltage across the gap drops in the process which produce a high conductivity between the two electrodes. So due to the, we have using the two electrodes, one is a positive electrode and another one is a negative electrode, right? So whenever we have a conduction, high conductivity between these two cathode, between these two plates, okay, so for that cases your current will be increasing whenever we have applied some voltage to the particular cathode or anode, whatever may be. So due to the high conductivity, so due to high conductivity, um, we will see our voltage is increasing as much. Okay, for that cases our current is also increased. Some of one is coming, I think. Okay, so our current is also green. This takes place a very short time. So whatever the process which will be takes place inside this particular helium gases, okay, that will be takes place in a very short duration of the time. So, okay, supposed to be at the time of t is equal to 0 to 1, okay, 0 to 1 per millisecond, right? So that duration will be very small. Okay, whenever we have to considering applied some voltages to the particular cathode or anode na, so there due to some high conductivity that there will be the certain increase of the current, okay, of a particular gas. That is actually the property of a helium gases inside the atmospheric air. Okay, and the time duration which will takes place due to this particular conduction, that will be very much small. Okay, so time will be considered as a microseconds. Okay, very small. Okay, so in the second part, what we will see, in the second part, it will be see that if the alpha of the primary ionization coefficient, as we can told you that alpha is your primary ionization coefficient. Okay, primary ionization coefficient, where beta is your secondary ionization coefficient, as we will told in the previous lecture, right? So if the alpha is the primary ionization coefficient for the applied uniform field E0, because this alpha 0 I told you that will depends upon your field intensity or the electric field intensity E0. Then what happened due to this particular effect of a particular alpha and as well as the applied uniform field. So for that cases, what is happened, that amplification of the ionization collision of the electrons which will takes place known as e to the power alpha x, right? Where alpha will be nothing but your ionization coefficient and x is actually the distance between the two cathodes. Okay, or we can say that it should be d. Okay, or we can say that it should be e to the power minus alpha d. Okay, so that is actually what is happened inside the particular helium gases. That will be the characteristics where we will see that due to the particular high conduction, what is happened, the current will be increased drastically whatever the voltage inside the cathode or anode. Okay, so in this particular cases, if this particular high conduction or the high conductivity alpha is the primary ionization coefficient that will be applied to the particular electric field intensity E0, and then amplification of the ionization collision of the electron will be given by e to the power minus alpha t. In this event of a positive ion space charge will be distorted in the field. Okay, so due to this particular conduction, what is happened, the positive ion which will be coming from the space, that will be distorted in the field, and for that cases the amplification of the particular primary ionization coefficient which will be known as alpha, which will be increased with the distance. So whenever the distance between the particular two electrodes will be increased, so for that cases the amplification factor of a primary ionization coefficient will be increased with the increase of a distance, and the time is given by this particular formula, okay, which is shown in this particular figure. Okay, this for formula. Okay, that means it will increase this alpha, the coefficient of alpha will be increased. How? The coefficient of alpha will be increased like this. Okay, so the exponential of integration 0 to d alpha of xt, because alpha is the function of x and t into dx. That will be the very important equation for calculating the voltage current characteristics of a coefficient alpha, okay, in a uniform field or in a applied uniform field E0, right? So integration 0 to 2 means supposed to be our distance will be vary from the 0 to d. Integration 0 to 2 means it will vary from, it will summation of vary from, that means distance will be vary from 0 to d. alpha of x of t. T is actually nothing but a time period. Okay, and x will be the distance between how much the electron will be travel from the cathode to anode. That one particular distance is actually the x defined. Okay, a small, or we can say that del x. Okay, del x is a very small distance between the two electrodes. Okay, supposed to be this is the middle portion. Suppose this portion will be supposed to be your del x. Supposed to be this is cathode and this is anode, right? So this portion, whenever the electron will be flow from the cathode to anode, so suppose in a some point that will be your del x. Okay, that will be your del x. That means small distance, and the total distance of a particular two electrodes supposed to be g. So that's why it should be 0 to d. Okay, integration of 0 to d alpha of x of t, alpha of x of t into dx. That is why. Okay, so now in such a cases, mu of t can be written, and mu of t is actually what? Mu of t will be nothing but another coefficient which will be considered as a helium ion, right? So for that cases it will be written as, for that cases it will be written as mu of t is equals to, this is called the helium coefficient, helium ion coefficient, right? Okay, so the mu of t will be written by a lambda into sorry, exponential of integration 0 to d alpha of xt into dx minus 1. Okay, so why this is minus 1? Because we are considering a distance of a small x. Okay, and the total distance will be my, sorry, yes, the total distance will be my d, right? So what is happen? So this portion, the total distance d, and the small amount of portion of x, that is minus of 1, supposed to be this portion. Okay, so that's why it is minus 1. Okay, so for that cases, what will be the lithium coefficient? That is mu 2, which will be defined as a, in this particular equation it will be defined, right? Okay, so what is written that, so till the breakdown, so whenever the breakdown will be occurred, after this breakdown it will not be happen. Okay, so before that breakdown will be occurred, so for that particular cases we will considering that particular equation for the helium ion coefficient, right? So now what is happened, we will considering this particular characteristics. So what the characteristics is, so the experiment has been performed to study a current growth. Okay, that means this particular profile is actually show the current profile. Okay, this particular profile which will show the current profile, right? So which will be show the current growth. Okay, which will be show the current growth of a, because this profile will be the current profile. Okay, that which will be so due to the high conductivity, that will show the current profile graph, right? So the now next what is happened, now it is written that the experiment has been performed, okay, to study the current growth in a uniform field in the air and other gases initiated by the single electron where n0 is equals to your 1, right? N0 is equals to 1 with the help of a light flash. The process with a higher number of electron, if whenever n0 is greater than equal to 1, for that cases it will achieved by illumination that cathode with a constant intense light. Okay, so for that cases, these are actually the two condition where n0 is equals to 1. What will be the behavioral condition of a helium? Okay, whenever the n0 is double greater than 1 or the greater than equal to 1, so what will be the characteristics which will shown in the cathode region, or if we will see in the helium electron, obviously, because we are considering the helium ions, right? So in the second part, this Hooger is actually the scientist, those who is developed this particular experiment for the high conductivity of a helium gases. Okay, so this Hooger which will develop one such method of a measurement of in a nitrogen. Okay, now Hooger will be developed this particular experiment not only in the helium gases but also the another the gases which will be known as a nitrogen, right? So in this particular nitrogen, what is happened with the help of the theoretical consideration confirmed with an experimental result. He computed the current growth started by a single and a more number of electrons. Okay, so that we will show in this particular figure. That is show I will show you in this particular figure. Okay, so how this particular, if I using the nitrogen gases, what will be the current profile? Okay, and what will be your voltage profile? That is actually shown in this particular figure, right? Okay, so the measured value are indicated by the vertical lines. Okay, this particular line measured value. Okay, this vertical lines which will be shown, this will be the measured value of a particular current profile for a particular instant of a time. Okay, because this profile will be considered as a time period and as well as whatever the current profile we will consider, right? So in the next part, which is written at a lower value of the current, keep in mind these things always, this point is very important. Okay, at a lower value of the current, the statistical distribution scattered more compared to the distribution of a higher current value. Okay, jitna tumhara lower current value hoga, then the distribution of a particular current profile that will more compared with the distribution of a higher current value. Okay, so if my current value will be higher, so for that cases our statistical analysis will be more comfortable. Okay, more applicable, right? So for that cases, what we will see that in this particular figure, that will be my current profile, which will be defined as an I of t at a particular time interval, and this particular profile which will be considered as a time at a 10 millisecond. Okay, but a particular microsecond, right? My mu s. Okay, and that will be your measured value. Okay, and that particular profile, that will be your current profile. Okay, so here it will see the calculated with a space charge. Okay, so here this all those things will be considered as a space charge calculated with a how much charge which will be gained whenever some voltage will be applied to the particular voltage which will be applied to the particular electrodes, right? So now this will be is actually your profile. Okay, current charge profile. Okay, calculated without the space charge. Okay, this portion you will see, this will be without the space charge, and this portion which will be show this particular indication, that will show the calculated with a space charge, and this will be non-calculated space charge. Okay, calculated without space charge. Okay, and that will be your experimental value. That which will show supposed to be this point, what will be at actually your particular time, this point what will be your particular time period. Okay, that we will show. Okay, so for this time what will be my for this time what will be my time period, and for this time for this time what will be my particular time period. Okay, that we will show in this particular figure. So what the particular behavior of the circuit profile or the current profile is actually the current growth initiated by the single electron. Okay, by the single electron, where your electric field intensity can be assumed as there will be some value which we will putting 44.8 volume per cm. Okay, so or we can say that the torque, and the distance between the two electrodes we will consider the 2 centimeter, where your coefficient will be, okay, primary ionization coefficient will be 12.3. okay, and mu will be considered as a semigraphonic plot. Okay, or we can say that mu is actually 1, or it will be greater than 1. Okay, so that is actually the value which will be assigned for constructing this particular experiment or for conducting this particular experiment of a nitrogen gas, right? Okay, of a nitrogen gas. Now this next particular characteristic is what? Now for the nitrogen gases, the movement of the charge carrier, that means the electrons and the positive ion in the gap, is represented by the growth of the circuit current. So the movement of this particular charge carrier, that will be defined how much growth of the particular current that inside the circuit, that which will be defined in this particular current profile, right? So the saturation level of the particular curve in the figure this, okay, is also called as a steady state region. Okay, steady state, because we have already know in the circuital analysis, we will know we have a two type of analysis. One is a steady state analysis, another one is a transient analysis. Okay, so steady state, after a certain period of time your current profile will be under the steady state profile, right? So that is why it will be assumed that the saturation level of this particular curve, okay, after a certain duration of the time it will be considered as a steady state region, right? And the third point is that if it is assumed that the number of the positive ion is diffusing per second at the cathode are just equal to the number of newly formed electrons. So whenever some of the electron which will be newly formed and that will be transferred to the anode to cathode, okay, or the cathode to anode, that will be arrived at the particular anode, and that will, for that particular flow of electron, the growth of the current in this particular region can be given as, okay, this particular formula, okay, can be given as I is actually the total current which will be flow across this particular conductivity. So I will be nothing but a I is actually the initial value of the current into e to the power alpha d, which we'll already discuss in the previous lecture, that the total current due to this particular high conductivity, okay, so what will be I0 is actually nothing but a initial value of the current, initial value of current, right, initial value of the current, where alpha will be the primary coefficient, okay, and d will be actually the distance between two electrodes, right, distance between the two electrodes. So for that cases this point will be very important, okay, this equation, okay. So whenever we considering the numerical analysis, all those equation you keep in mind, because this particular equation will be considered whenever you have to deal with any such kind of problem related to particular ionization effect, right? So now here it will see that the initial current, initial photoelectric current at the cathode, right? So now in the next point, although this expression represent the average effect of a number of avalanche, it falls signify in the breakdowns. Okay, this particular equation is also known as a avalanche breakdown equation, as it will considered in a high conductivity region. Okay, so the current in this particular region 3 has much steeper rise till the breakdown will be occurred. So due to this particular breakdown, okay, so what is happened, there was due to this particular breakdown which happened in the particular region, so what is happened, this particular steady state condition will be takes place of this particular current profile, right? So in this particular cases, the Townsend current growth equation in this particular reader can be defined as this particular equation, okay, Townsend current growth equation. It is known as a Townsend current growth equation. So it will be defined as a N0 double dash is equals to N0 plus N0 dash, right? N0 dash. Okay, so this one. Okay, where N0 actually nothing but the number of primary electron emitted from the cathode whenever x is equals to 0, right, per second, okay. And in other word, an avalanche N0 actually what is the number of the primary electron which will be emitted from the cathode, okay, at a distance of x equals to 0, okay. Now N0 dash which will be nothing but the number of the secondary electron which will be produced at the cathode. This will be emitted from the cathode and this will be produced by the cathode, okay. So the number of secondary electron that will produce at the cathode per second, and N0 double dash is actually what, the total number of electron that will be leaving the cathode, okay, that will be leaving the cathode. That means this N0 will be the number of electron which will be emitted from the cathode at a distance of x equals to 0. N0 which will be nothing but a number of the secondary electron which will be produced by this particular cathode, okay, and N0 double dash will be nothing but the number of electron which will be released or which will be leaving from the cathode per second. So thus the equation will be constructed as N0 double dash is equals to N0 number of electron produced, sorry, the number of electron emitted at a distance of x plus the number of electron which will be produced due to the cathode per second, okay, due to this particular cathode per second. Now what we will see, that in this particular equation, since each electron leaving the cathode makes an average, So for that cases, what we will see, that means e to the power alpha d. So for that cases, we will consider that this e to the power alpha d minus 1, that is actually the distance. Okay, since the electron leaving the cathode make an average collision at a gap d. Okay, at a gap d, therefore the total number of ionization collision per second in the gap will be what? N0. That means we are finding the values of this. So N0 double dash into e to the power alpha d minus 1. Okay, so you will consider this equation. If we will consider this equation, that means this equation will be termed as a e to the power alpha d minus 1. So that is this minus 1 and this minus 1 will be considered as a same equation. Okay, if we derive exponentially, then it will comes this equation e to the power alpha d minus 1. As we will consider the number of total number of electron which will be leaving from the cathode, so at a distance of at a collision gap at a distance between the d, so for that cases our equation will be constructed like n0 dash n0 double dash e to the power alpha d minus 1. This equation is also very important. So the now so by the definition, if the lambda or if this one is actually your secondary ionization coefficient. So for in case of a secondary number of the secondary electron produced by the average cathode per ionization collision in the gap, then this equation can be converted into n0 dash is equals to lambda of n0 double dash e to the power alpha d minus 1. Right, this equation. Right, so this equation is also very important. If we will consider this one is the number of the secondary electron which will be produced in the particular cathode. Right, so now if we substitute in this equation and equation, this is equation supposed to be 1 and this is supposed to be equation 2. So if we substitute in these two equations, so we will have this equation. This equation is actually n0 double dash is equals to n0 plus lambda of n0 double dash e to the power alpha d minus 1. This will be actual main equation whenever we have to consider the tungsten current growth equation. Okay, tungsten, where n0 double dash is actually nothing but the total number of the secondary electron which will be leaving from the cathode per second. Right, which will be leaving from the cathode per second. Now if we simplify this particular equation, then it will get n0 dash. If we simplify this equation, then we will see that n0 double dash will be nothing but a n0 1 minus lambda of e to the power alpha d minus 1. This equation, right? So from this equation, supposed to be this is equation supposed to be 3. So from this equation, we can see that. Yes, so from this equation, the number of electron which will be arrived in the given as nd supposed to be nd is actually nothing but a n0. nd actually nothing but a distance between the two electrons. Okay, so the number of electron arrive at the anode section, that will be defined as this equation. Okay, when the nd is equals to n0 into e to the power alpha d. So by putting the values of the 00 for the above equation, then we will get, now we will put the value of this particular n0 dash, which will be this. Okay, so now if we put this, so what will be my value? So n0 e to the power alpha d divided by 1 minus lambda e to the power alpha d minus 1. If we simplify, if we put the values of n0, then we will get what will be the values of nd. Okay, so under this particular steady state condition, the current in this gap can be therefore given. So what will be the total current due to this particular electron gap? Okay, so that will be your I is equals to I0 e to the power alpha d divided by 1 minus tau of e to the power alpha d minus 1. That is actually the total current which will be flow due to this particular conduction. Okay, of or the collision of between the two electrodes. Right. So I think we will discuss the next part. That in this part will be remain. Okay, so I think we will stop the session for today. Okay. So if we have any queries right now, please tell me, because this equation will be very important whenever you have to deal with the numerical analysis. Okay, although it will be not in the syllabus of a gate. Okay, but whenever you have to, for the understanding purpose, and whenever you go for the industry, then this particular applications area will be huge, right? So that is why this particular components of this particular equation is necessary for the calculating what will be, for calculating the equation, or the calculating the high voltage components, or the for measuring some high voltage appliances. Okay, so that is very important. Okay, so the next class we will discuss some more thing regarding the conduction of a electron whenever we have considering the two electrode at the distance between the d. Okay, so I think we will stop the session for today. We will discuss in the next class. I think tomorrow I have a class. Okay, then we will discuss the next one. Okay, thank you very much. Now we will stop the sharing. Now those who have joined, kindly leave the session and we will discuss in the next part.